Hello, sorry about that, guys. I started the wrong broadcast. That's what happens when you have multiple broadcasts all scheduled for the day. Right, okay, guys, this is going to be the end of water for acid-base theory. We're going to finish off water today, get that all boxed off. As I said, I'd really like it if you guys could contribute on the chat as much as you can. That would be grand. I'm just going to wait until there we go, and then I can pause that. You guys know that you can, there you go, paused it. You guys know that you can up the resolution using the little cog button at the bottom to make sure that you can get as better quality as you can. Right, I'm going to share my screen with you guys. Share screen, share screen, share screen. There we go. And then I'm going to go that one, not my face one, don't want my face one. Oh, that's stupid. Okay, next I'm going to have to recreate that on the stream, aren't I? Oops. See. Right. Okay, so back to this. So last lesson, what we did was we had a big long chat about water. We talked about the ionic product. So we talked about the fact that water has these really cool properties. It's always neutral because the H plus and OH minus concentration is always the same. We talked about the ionic product of water, the fact that water dissociates. We then talked about Bronsted-Lowry as proton is all about proton transfer. Then we talked about Lewis, and the idea that the Lewis is about electron transfer. We then looked at various scenarios, did a various set of questions, and then we talked about the equilibrium of water and how it would change the pH. So that's what we ended up on. And today's lesson, we're going to finish off water, get that all boxed off. Oh, Emma's here. Oh, I'll mark Emma in on the register at the end of the lesson. Right. So today we're going to pick up KW. Sorry, my laptop is struggling just a little bit. So we've got 3 learning objectives. 1, understand KW. Number 2, to be able to use KW to calculate the pH of water, and then understand dilutions. That's my plan today. Okay, so title is KW. So first thing is KW, the equilibrium constant for water. Now, at this point, I now need to give you a value. And guys, I'm really sorry, you've got to learn this value. Yeah? So the equilibrium constant of water at 25 degrees Celsius is 1 times 10 to the minus 14. And I'm going to show you where that comes from. We're also going to create its units. So units, question mark, we'll come to that. It's always nice to apply our understanding of KC to be able to work out units because they do that an awful lot. So unfortunately, guys, I'm going to put this in a nice sparkly red box. There you go. My laptop pausing there. Guys, learn this. Yeah, you've got to have that value in your head. Learn. So that is KW at 25 degrees Celsius. Okay, so where does KW come from? So this is based on an equilibrium constant. What that means is that we can look at the dissociation of water, the dissociation of water, and we can write our equation. H2O going to H plus and OH minus. Yeah, we can get our dissociation equation. Then what we can also do is therefore create a Kc from it. Now Kc is the equilibrium constant. Now what you guys can now do is, if you could create your equilibrium constant, I'd love, would somebody be able to have a go at trying to post their equilibrium equation, their Kc expression, yeah, Kc expression on the chat? That would be amazing. Now, so you guys are going to have a quick effort at filling that out and lobbing it on the chat if you can. I know it's tricky because you can't write equations. All you can do is write them. Yeah. So have a go at writing the Kc for water. Now, it's really nice to talk about Kc. Yeah, there we go. I love it. Now, Ben, well done. You missed the square brackets around the water. Yeah, and you also missed the letter of Kc out. It is really important that you incorporate Kc into your expressions. So Kc equals, you can't miss that bit. Yeah, it's important that you don't, otherwise it doesn't mean anything. Yeah, thank you very much, Nikita, that's outstanding. So we have products over reactants. Amazing. OH minus all over the concentration of water. Okay, now the next thing to talk about is the fact, well, we know that the dissociation of water is tiny. Yeah. By the way, it doesn't look like tiny. I'm going to clean that up. Is tiny. Yeah. So what that tells us, it tells us that this equilibrium lies heavily to one side. Now, how do we know this? We know this because I've given you a kW value. Yeah. Now, kW is Kc. It's just it's the water version. It's special. So we can say that the equilibrium lies heavily in. Oh, blimey! Let's try that again. And I love that I'm using blue. See what I'm doing there? Yeah. Oh, darn it! Try that again. Yeah. It lies heavily. That doesn't work either. I don't like it. Let's go pen. Hello, pen. Come on. This is where my laptop really is struggling a little bit to be able to keep up with me. Yeah, doesn't work as fast as I do. Come on. There we go. It lies heavily in this direction. We know this because the kW value is minuscule, and we know that Kc is linked to products. Yeah, the equilibrium, and we can write this, the equilibrium lies heavily, it's not very truthful, is it? It's not very honest. See what I'll stop. Equilibrium lies heavily to the left because value is so small. 10 to the minus 14. Holy mackerel, holy moles. That lies heavily to the left. Right. So at this point, what we can do is we can now rewrite our expression, switch back to black. We can rewrite our expression for Kc. Yeah. And what we realize is that the concentration of water, this value here, is massive. Absolutely massive. The top numbers are tiny, but the bottom number, the concentration, is enormous. Now, I'm actually going to run that question in a minute just to show you guys just how big it is. Now, in mathematics, I'm going to come back to that hand. So it's so big, the concentration of water, concentration of H2O is so massive, so huge that it can be considered, it is effectively considered, ... mathematicians in the room, that if a value is so large, yeah, and I mean like enormous, it's like 55 molar. It is insane. If a number is so big, what would that mean that value would become in mathematics? What would you call it? Let's see how long it takes. If anyone can post on the chat, by the way, on that particular question. It can be considered. Wonder if anyone can get it. I'll wait for just a second. Have I just lost Ben again? Ben's got Wi-Fi issues. Okay, it can be considered constant. Can be considered constant. It's so massive, no matter how far we push the equilibrium, it just doesn't change enough to actually see a difference in that value. Now, what that means is I now have an expression with two constants in it. In mathematics, we don't like this. What do you do with two? Now, I'm going to flag these up now. We've got a constant and a constant. I should be doing blue, really, shouldn't I? Yeah, if I've got two constants, when you say the concentration of water, is it like the concentration of water in water or given as a volume? Okay, Ben. Sorry, Ria. It's got this because they're both in pink. Okay, good question. So this question I'm going to do now, this is just purely for fun, but it's never been asked on an exam, but it got asked on an Oxford interview for a student of mine a couple of years back. Not a couple of years back, quite a few years back. So what is the concentration? What is the concentration of water? What is the concentration of water? Question mark. And now this is a beautiful chemistry question, because at this point, by the way, I'm actually going to ask you guys if somebody fancies a challenge. Somebody really fancies a challenge, and I'm talking, this is an Oxford interview question. You can pause the video now and have a go at it. Yeah? And then you can unpause it and then see what the answer is. So here's where the answer comes from. So number one, concentration equals moles per dm cubed. Okay. So what we now need to do, we need to work out the number of moles in a liter. Okay, number two, 1 liter, 1 dm cubed of water of H2O equals 1 kilogram. We can then convert that into grams, which is 1,000 grams. So number of moles is grams over rams. So I can now go number of moles is 1,000 grams over 18.0, the relative molecular mass of water. Now that's going to spit out, this is, by the way, I left my bloody scientific calculator at school. Absolute fiasco. Should never do this. Now I'm going to have to go and buy myself a new one. What I'm going to do is I'm just going to quickly find the calculator on my phone. 1,000 divided by 18 gives me equals, so I have 55.6 moles of water in 1 kilogram. Oh, well, hang on a minute. That's now my concentration because we took 1 liter. So I've got that many moles. So the concentration of H2O in H2O equals 55.6 moles per dm cubed. That's mental. The most concentrated sulfuric acid you can get to is 16 molar, and that's considered conc. That's terrifying. And this is 55. This is just orders of magnitude bigger. It is so large, it's effectively constant. Yeah. So, okay. Now in mathematics, if you have two constants, we don't like two constants. What we're going to do is we're going to combine it. We're going to reorganize the equation and go Kc constant multiplied by the water concentration constant equals H plus concentration multiplied by OH minus concentration. Well, the great thing is those two values are both constants. You will form a brand new constant, and hence Kw. Kw, no problem, Maria. I'm glad that you enjoyed that tough question, right? Kw is equal to the concentration of H plus times concentration of OH minus. How cool is that? Kw is a brand new constant. Yeah, it is a spin-off of Kc, but we've actually combined two constants together. And by the way, that question has been asked. It asked you to derive Kw. Yeah, so they asked you to write the original Kc. Then they asked you to explain. So the original case said step one, write the Kc value. Then it said, then what do we know about H2 concentration? And you then say that the equilibrium lies heavily to the left. So the value is so large, it's constant. Then you combine the two constants to create a Kw. It was amazing. Love that question. It's tough, man. So Kw is very special. You guys now need to learn this. That's important. Okay. So the next thing is, I want to show you guys something really cool. So I'm now going to quickly have, you guys are all on your video cameras. So all the video cameras are on. Mika, Dat, and Nikita have turned theirs off for a second. Guys, can you hold up your hands, please? And can you give me the pH of water at 25 degrees Celsius, please? Using your hands, hold up your hands and show me the pH of water at 25 degrees Celsius. You're going to love this. This is, of course, straight out of year 7. Can you believe it? The last time they used this number. Yeah! Look at that. All the hands are up. All the hands are up. I don't. Oh, I love Ivan. You mirrored. Flip your hand round. Flip your hand round, Ivan. Well done, guys. It's 7. So you guys learned. How cool is this? I love this. Let's go back to year 7. Year 7. Whoa, that's a bit fat, that. It's a bit fat. In year 7, pH of water is 7. Now, at this point, woo, it's the same as the year group. It's cool. I'll stop. So the pH of water is 7. Well, now we can prove this. Check this out. So at 25 degrees Celsius, I gave you a kW value. kW equals 1 times 10 to the minus 14. Check this out. Now we've got an expression. kW equals H plus and OH minus. Right, well, we know that the kW value will slot in there. Now, here's the cool thing. We can now say that because we know the dissociation of water is a 1-to-1 equation, assuming nothing else is there, the concentration of these guys is the same. We can therefore produce a false expression. Now, this is false. This is only used for calculations. The false expression. Yeah, the false expression is kW equals H plus squared. Check this out. So if I want H plus, I root kW, because I root the other side as well, and I'll get the concentration of H plus. So now I can input my value, 1 times 10 to the minus 14, root that number, and I will get 1 times 10 to the minus 7. Now I've got the H plus concentration. Now I can minus log it. Minus log answer. And look what I get. Oh my God, isn't that just absolutely amazing? It gives us the year 7 pH value. Holy guacamole. Guys, does that give anybody goosebumps? It gives me goosebumps. Isn't that amazing? Like, you learned that in year 7. You have no idea about where that value comes from, but whoa, that's so cool. Yeah, it isn't just, we're not just teaching you these things in year 7, just, for fun and games. We are laying the foundations of year 13 chemistry, the hardest chemistry you're going to ever be sitting at A-level. This be crazy, man. How cool is that? I absolutely love it. Gives me goosebumps. I love chemistry. Chemistry is wonderful. Cool. So now that we can use kW, we can do some really cool things with this. So we can now change the value of kW and work out the pH. So here are the questions. So the first thing is no kW. We've got it. First learning objective ticked off. Use kW to calculate the pH of water. Right. Question number 1. So these are taken directly out of A-level papers. So question number 1, define the term kW. We can all do this now. kW equals H plus concentration times by OH minus concentration. Define the term pH. We can all do this. Minus log to the base 10. You don't actually need that, but it's nice to do so. pH is the minus log to the base 10 of the H plus concentration. I actually prefer writing pH equals. I prefer that. Next, calculate the pH of pure water at 50 degrees Celsius. Explain why pure water at 50 is still neutral, even though the pH is not 7. Guys, look what they've told us up here. I'm going to go for blue because it's water. It has a new value. It's got a new value. Now, if it's changed the value, we've changed the pH. So, guys, on the chat, please. Using your calculators, I'm going to give you guys a moment to do this. Can you give me the pH of water at 50 degrees Celsius, please? Off you go. We'll give you a minute. Have a go at doing it. In fact, guys, pause the video. Pause the video at this stage. Have a go at calculating it. Unpause it when you're done. Okay, so Let's run it. Let's run it. So KW equals H plus bracket and times by OH minus concentration. Therefore, false expression. KW equals H plus squared. Right, I can go therefore. KW root KW will give me H plus concentration. Right, input my values. So root 5.48 times 10 to the minus 14 gives me H plus concentration. This is where I now need to run it through on my calculator. This is where I'd really, really like to have an actual calculator. I do have one in my, I've got a scientific one that I can try and use. Okay, got it. So I'm going to go root 5.48 exponential minus 14. And I get 2.34 times 10 to the minus 7. And I'm now going to minus log answer. And I get minus log, oh, no. This is on my calculator on my phone, just doesn't do it. Equals. I just want as equals. Got it. Right, I've got, it doesn't let me do that. Right, minus, where are you? Oh no, I found the log button. Minus, no. Uh-oh, it's not letting me do it. Right, 3.4 times, okay, I'm just gonna keep that. I'm gonna get rid of that number because I promise it's not letting me keep my number. So I'm now going to do minus log 2.34 exponential minus 7. And I get a pH of 6.63. Check that out. Can I have a, oh, look at Nikita. Nails it. Well done, Nikita. Great job, star. And this makes total sense. Because if I raise the temperature of water, looking back at our equilibrium and our understanding of this, we know, we're going to switch to blue, we know that when we're, oh, this is where laptop's not quite as quick as I am. So in this equation, we're breaking bonds here, yeah? And if we raise the temperature of water, yeah, we're going to break more bonds. So the equilibrium shifts this way. The H plus concentration will therefore increase, therefore the pH will decrease. Can everyone give me a thumbs up if they got pH 6.63, please? Amazing. Right. How cool is that? It's amazing. Cool. I'm going to give you one more. Oh, hang on. We didn't ask an explanation. So it then says, explain why it is pure water is still neutral, even though the pH is less than 7. Yeah, and of course, the reason being is the concentration. This is where I'm going to switch back to black. Concentration of H plus and OH minus, not and. Oh dear, it's not going well. H plus and OH minus are still the same. Isn't that cool? I love it. I'm loving it. Next. Okay, so it's just nice to show you this one. Write an equation that represents the dissociation of water. Dead easy. Everyone can do this one. Can you pause the video, please? And can you run through these questions? I'll put them all there. In fact, this is where it'd be nice. I'm going to do it bit by bit. I'll give you that bit there for now. Right, guys, pause the video. Off you go. So, H2O, equilibrium. How many people are going to forget the equilibrium symbol? I wonder. Yeah, easy bit to miss. Give an expression for the equilibrium constant Kc for the reaction in C1 and use this to derive the expression of Kw. 3 marks. Kc equals H plus times OH minus all over H2O. Second mark, concentration of water is so large, it is effectively constant. Two constants get combined, combine constants. Kc multiplied by H2O gives H plus, OH minus. Therefore, these get combined to give you Kw equals H plus multiplied by OH minus. Nailed it. Isn't that cool? Isn't that lovely? Yeah. Next, the ionic product of water is this at 313 Kelvin. Calculate the pH. Kw equals H plus multiplied by OH minus. Right, false expression, Kw equals H plus squared. Right, therefore, root Kw gives me H plus concentration. Input my numbers. Root 2.92 times 10 to the minus 14 gives me H plus. There's my next mark. Do it on my calculator. Okay, AC root 2.92 exponential minus 14 gives me 1.71 times 10 to the minus 7 minus log answer. Minus log answer. I'm just going to get rid of that on my calculator because I can't do it. Minus log, I would have kept it on my calculator otherwise. 1.71 exponential minus 7. And I get a pH of 6.77. And there's my answer. Winner. Nailed it. 6.78. Thanks, Donna. You probably used your calculator. It's going to be the same answer. Yeah, I couldn't keep that number. I couldn't keep that on my calculator because I'm using a stupid phone calculator. Stupid. Your answer is probably the better one. Cool. Next, give the pH of water. Given that the pH of water is, state whether dissociation is endothermic or exothermic. Give the reason. Right, dissociation. So it's going to be endo. Yeah, we know this. It's going to be endothermic because we're breaking bonds. This is mexobendo. Endothermic due to dissociation. Dissociation. French for dissociation is breaking bonds. And we're done. Breaking bonds. By the way, they also want us to use the previous answer. Yeah, is breaking bonds. So I'm going to add in a second point, which says at higher temp, more H pluses are produced. More H pluses are produced, so must be endothermic. That's it's a famous song. That yeah, it's the endothermic song. Cool. So at this point, guys, we can go winner. We can now use Kw to calculate the pH of water. That's French for water. So the next one is dilutions. Okay. So, check out my beautiful set of chemistry notes. Isn't that gorgeous? Just beautiful, beautiful chemistry. It's stunning chemistry, actually. Love water. Right, guys. New subtitle, please. Dilutions. Cool. So, dilutions. Bless you, Nikita. I've just looked up and seen you sneeze. That was amazing. So, in dilutions. So, equation. Now, you guys have got grams over grams, C times V over 1,000, PV equals nRT, all that jazz, and all that jazz. You've got a new one, which is C1V1 equals C2V2. So this is, sometimes people prefer to do C ori, and that stands for original. C original times V original equals C new times V new. Can I just say that this equation, C1V1 equals C2V2, is the most useful equation I will ever teach you. Because I know that most of you are going to go on to do a degree which has nothing to do with chemistry. But this equation, oh my God, is it useful. So I need to explain to you why this can be used. Yeah, just to show you where it derives from. Yeah, deriving. So if we have a beaker of solution that contains hydrochloric acid, HCl, and we're going to call it 1 molar, 1 mole per dm cubed. What we know is if we add water to this, yeah, water has no acid-base properties. No acid-base properties. What that means is it is not going, no acid-base properties, it is not going to remove any of the HCl's in the beaker. What that means is, therefore, the moles of HCl remain the same. So what that means is you could, if we're going to now add water to this, let's compare two beakers. Let's actually make the pictures a little bit believable. Yeah, HCl, 1 mole per dm cubed, and I'm going to give you 50 centimeters cubed. What we're then going to do is we're going to add some water. Yeah, add water, add H2O. And what we're then going to have is a beaker with HCl, but this time the concentration will now change because I have diluted it. Yeah, but I now have a new volume. Let's double it then. Let's double it. 100 centimeters cubed. Now what that means is, because the number of moles of HCl is still the same, for each one, I could do number of moles for let's color code this. Yeah, for this guy, the number of moles is C times by V over 1,000. For this guy, it is C times by V over 1,000. But the great thing is the numbers are the same. Now, if the numbers are the same, we can get rid of the letter N. So we now go, C times V over 1,000 is equal to the new C times V over 1,000. Now, the great thing is, if we move the 1,000 of one of them over to the other side, I'd times that both sides by 1,000, and the 1,000 cancels out. Isn't that nice? So we end up with a brand new equation of C1V1 equals C2V2. So now all we need to do is run my numbers. So I had a concentration of the original of 1 molar. C1 was 1 mole per dm cubed. 1 mole per dm cubed. The V1 was 50. My new concentration is the question mark, but I'm timesing it by 100. Bring the 100 over to the other side. So I've got 1 times by 50 over 100 will give me my new concentration, which is going to be 0.5. So I've halved the concentration. And the great thing is, minus log answer because it's a strong acid, and I will get the new pH. Isn't that amazing? I love this equation. Oh my God. It's the most useful thing I will ever teach you. Yeah, you may even use it in everyday life. I highly doubt it. But you can. Yeah. It's a really cool equation. So at this point, let's do some questions, folks. Now that we've got all that down, I don't want to rush you guys through this. I love these questions. They're amazing. They're just run C1V1 equals C2V2. You nail it. Right, question number 1. So question number 1. Let's zoom in. So I'm going to make it easy, and then I'm going to make it harder. So question number 1. Nikita has 100 centimeters cubed of 2 moles per dm cubed, 2 moles per dm cubed HCl, brackets aqueous. She needs 0.175 moles per dm cubed. What total vol will she make it up to? Pause the video and answer my question. As soon as you've solved it, post it on the chat and then check your answer. Cool, we're doing well. Right, you've all paused. Now you've unpaused. So I'm going to make my pen a little bit thicker. Maybe. Yeah, I'm getting bigger in my writing. Shouldn't do that. So answer. My laptop is just taking a few moments just to change over things. Right, it's a dilution. I'm adding water to it. Yeah. She needs what total vol, I'm going to put of water, of H2O, will she make it up to? Right, we're adding water. This is clearly a dilution. Okay, so C1V1 equals C2V2. The question is asking me for the new total volume. So I'm now going to reorganize for it. Therefore, C1V1 over C2 gives me V2. Right. Now I can insert my numbers. Nikita's original concentration was 2. She's times by her original volume of 100 centimeters cubed. And she wants a concentration of 0.175. What's the answer? Just becomes 200 over 0.175. So answer is 200, nope, AC 200 divided by 0.175. She needs to make it up to the new total volume of 1,143 centimeters cubed. I love it. Isn't that cool? Yeah, I love it. Look at Ria, look at Dana, look at Nikita, smashing it out the park. Well done. Thank you, guys. Really impressed. Are you ready for the slightly harder question? Let's step it up a level. I love how you can rank them up. Question number 2. Dat has, let's go right HCl. Dat has 50 centimeters cubed of HCl pH 1.2. He needs the HCl to have a pH of 2.6. What volume of water will he add? Question mark. Right, guys, pause the video. As soon as you've found your answer, post it on the chat. I've still only got 3 people contributing on the chat. I'd like to see a few more if that's possible. You shouldn't be unclicking the video until you're ready to post, but I don't mind. It's, I get it. These are tough. Right. Unpause your video. Here's the answer. Okay. Now, this is really clever. We know that this is a dilution. So I need C1V1 equals C2V2. Now, there's a trap in here. The reason being is we haven't been given concentration. Or have we? We've got volume, there's my V, and we have been given concentration in the form of pH. We need to take it out of pH. Step number 1, 10 to the minus pH will give me the concentration of H plus ions. This is much harder, folks. The Dat thinks he's already solved it. Wow, I don't like your little power thing there, Dat. 10 to the power of 1.4. What? Dat, are you having a laugh? What volume of water? Can I have a real number, please? What's that? What junk's that? Weird. Right, so on my calculator, shift 10 to the power of minus 1.2. Right, so therefore, the concentration of H plus is 0.0631 moles per dm cubed. Right, this is now C1. But now I need to find C2. Can't do this without C2. And they've given us a new pH. That's C1. This is C2. Right, so I need to do 10 to the power of minus 2.6 equals, right, on my phone. So shift log minus 2.6. That now gives me 0.00251 moles per dm cubed. That now is C2. Okay, now I've got V1, I've got C1 and C2. I can lob them in. Now there's an extra kicker on this. So the C1 V1 equals C2 V2. Input my numbers. C1 is 0.0631 multiplied by V1. What was his original volume? 50 centimeters cubed equals C2 V2. Now I've got the C2 is 0.00251 times by V2. Now remember, there's a clause here. That's the total new vol. Yeah? So reorganize. Divide both sides by the new concentration. Right. Run that through my calculator. So 0.0631 multiplied by 50 equals. Right. Divide that answer by 0.000251 equals. Right. V2 equals 1257 cm cubed, because I was in cm before, so it'll spit out cm after. Now there's a trap here, because that's not the answer. That's not the answer. Kayun's got it right. Well done, Kayun. Yeah, well done, Donna. Smashed it. Because what you need to remember is the question said, what volume of water will he add? Wow, scammed. So what we now need to do is minus the original 50, and we get a volume added of 1,207 centimeters cubed. Well done, year 13. And that brings me to the end of my beautiful water. Oh, I love water. It's just such wonderful chemistry. So great. Look at that. We're done. Outstanding. Right. Let's go back to my YouTube channel. Go back to that guy. End share, stop sharing. There we go. I'm back. Yeah. Guys, well done. That brings us to the end of water. Now, I'm going to post on your Google Classroom your homework. So I'm just going to post a couple of sheets to do with water. Yeah, just some water calculations for you guys to run. I hate water. I like apple juice. Apple juice has so much sugar. That's so true. So true, Donna. So true. Right, I'm going to end that here. Guys, bear with me. I'm going to appear on the chat momentarily. I'll see you guys soon. Right.